Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Renewable Hydrogen from Wastewater, a Water Corporation and Hazer project. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and to their cultures, and to elders past, present and emerging. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Water Corporation. Water Corporation is the principal supplier of water, wastewater, drainage and bulk irrigation services in Western Australia to hundreds of thousands of homes, businesses and farms. Water Corporation directly employs more than 3,400 people across the state, providing a high level of expertise and strong commitment to communities. Water Corporation manages $38 billion of assets that support in delivering water services across an expanse of 2.6 million square kilometres. Today, we'll hear from two speakers, followed by our live audience Q&A, and I encourage you to send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Russell Lamb. Russell is a chartered mechanical engineer and infrastructure procurement specialist and has 30 years of experience advising large-scale, complex economic, social and utility infrastructure projects across the UK, Singapore and Australia. Russell leads the infrastructure markets business at Water Corporation. This team is responsible for exploring and delivering innovative projects that provide value for money, along with overseeing the government's market-led proposal policy, which encourages the private sector to work together with Water Corporation. Please welcome Russell Lamb.
Hi, good morning. Thank you, Megan, for the introduction and the opportunity to present today. I'd also like to acknowledge the traditional owners of the land that I'm representing today in Perth, the Whadjuk Noongar people, and I pay my respects to their elders past, present and emerging. It's an honour to be presenting on Whadjuk Whadjuk. I'll be presenting on Water Corporation's collaboration with Hazer on the commercial demonstration plant project that produces hydrogen from wastewater at the Woodman Point, Worth. For those not familiar with Water Corporation, I'll start with an overview, then some information relating to the Woodman Point Worth, and then specifically the Hazer collaboration. Water Corporation delivers water, wastewater, drainage and irrigation services to approximately 1.3 million homes and businesses across the state, utilising an asset base of $17 billion. Just to put that into context, the state is 11 times the size of the United Kingdom. That's England, Scotland, Wales and Northern Ireland. So huge. Statewide, we provide 375 gigalitres of drinking water. That's 375 billion litres of drinking water. And we treat about 165 gigalitres of wastewater per year. Our purpose is to manage water services sustainably to make WA a great place to live and invest. The collaboration with Hazer goes to the heart of our purpose. We are made up of a very large integrated water supply scheme, which provides around 300 gigalitres of scheme water per year to about 90% of our customer base across metropolitan Perth, the Southwest, Great Southern and the Kalgoorlie pipeline. In addition, we have almost 100 regional water and wastewater treatment plants across WA, which vary significantly in size and availability of source. On the slide, you can see the location of the Woodman Point Water Resource Recovery Facility, or WRF, in the south of Perth. Water Corporation has recently changed the names of wastewater treatment plants that beneficially reuse or recycle byproducts of the wastewater treatment process. And they've changed it to Water Resource Recovery Facility, which better describes the function as well as the change of perception of wastewater. Wastewater really is a misnomer, and hopefully this presentation will in some way help to explain why that is. Woodman Point is the largest wastewater treatment plant in the state, currently treating 145 million litres of wastewater per day, with an ultimate capacity of 180 MLD. The plant serves approximately 725,000 people in the south of Perth. The plant consists of conventional, preliminary, primary and secondary treatment processes, integrated with a sludge management facility, which I'll explain more during the drone footage on the next slide. Due to its size, Woodman Point includes anaerobic digestion of sludge, which produces biosolids for reuse, and biogas. It is this biogas that is the reason behind the collaboration with Hazer. 100% of the 65 tonnes of biosolids per day that are produced at Woodman Point are reused as a fertiliser for agriculture. Next up, we have some drone footage of the Woodman Point site, and I'll talk you through the different elements of the plant as we go. The footage starts with us at the north end of the site, travelling south. We are now approaching the primary settling tanks in the middle of the screen. There are 8 long tanks or channels with a green inner cover and a white outer cover. Maintenance is being undertaken on the 4 tanks to the right. The primary settling tanks work by moving the wastewater slowly along the length of the tank, allowing the larger solids to fall to the bottom of the tank, where they are collected by a scraper that pushes all of the solids to one end, where it is collected and moved to the digesters. Now we are looking at the odour control system that pulls high sulphide odorous air from all parts of the plant. There are 10 bioscrubbers to the right and 4 chemical scrubbers to the left. The tall stack discharges the scrubbed air to atmosphere. In front of us at the top of the picture is the large dissolved air flotation tank. Mixed liquor enters the tank in the middle and makes its way via submerged channels to the white bubbly areas at 3 o'clock, 6 o'clock, 9 o'clock and 12 o'clock. The wastewater then travels around the outside of the tanks with air bubbling through the mixed liquor, attaching itself to the lighter solids that are floated off into a gully around the outside and are then sent to the digesters. Airflow into the mixed liquor is controlled by a feedback loop based upon the amount of ammonia present. High levels of ammonia would trigger more air, and vice versa for low levels of ammonia. The white ducts extract odorous air from the centre section that is anoxic. The air is taken back to the odour control system we just saw. The mixed liquor then travels to the 8 clarifiers, which allows the remaining solids to settle out. To provide some sense of scale, these clarifiers are 50 metres in diameter and 6 metres deep. You can see the empty clarifier on the right. Solids that settle to the bottom are removed through suction scrapers on the floor of the tank. We also just passed the overflow storage dam on the right. We're now travelling north back up to the egg digesters. The digesters are used to anaerobically digest the sludge into biosolids and produce biogas. To the right, you can see the gas holder and the two flares next to it where excess biogas is burned. We can now see the Hazer plant, which Luc will cover in more detail in his presentation. I hope you enjoyed the footage. The egg-shaped digesters use anaerobic digestion by bacteria to reduce pathogen loads in the biosolids and produce biogas. The 900 normal meters cubed of biogas contains 60% methane and 40% CO2 plus contaminants, such as hydrogen sulfide. Due to the process used, it is a renewable source of methane. The biogas is stored in the gas holder at the top. Under normal operation, the biogas is used as fuel for 3 reciprocating engines, which produce heat in the first instance to heat the biosolids to over 40 degrees C to enable the bacteria to do their work, and also to produce electricity, which is used by the site. The biogas provides approximately 40% of the energy requirement for the site. Any excess gas is flared to the left of the gas holder. As all of you will know, hydrogen has been a large focus for national and state governments for several years. This slide provides some details of the strategies, task forces, and funds announced at national and WA level. Hazer Group approached Water Corporation in October 2018 with a proposal to use the flared gas to produce hydrogen and graphite in the commercial demonstration plant project. The Hazer technology is different to conventional technologies to produce hydrogen, such as electrolysis and steam methane reforming. The Hazer process does not require large quantities of water as feedstock and for cooling, nor does it produce carbon monoxide or dioxide. The technology uses thermocatalytic decomposition of methane present in the biogas using iron ore as catalyst, but more of that from Luc later. Looking at the emerging hydrogen industry in general, the corporation could play in a number of areas, both directly and indirectly. Considering how the corporation could be directly involved first as a hydrogen off-taker, the corporation could replace diesel consumed by our vehicles and diesel generators with hydrogen. The corporation consumes almost 6 million litres of diesel per year. The corporation could become more involved by leasing land and providing water or biogas to an industry proponent as a hydrogen facilitator. The corporation is one of the largest landowners in the state, requiring land for current and future infrastructure. Some of this land, such as in the buffer areas around our wastewater treatment plants, could be used to accommodate solar panels, wind turbines and batteries to provide energy for hydrogen production. The corporation obviously has access to water, so this could be sold to the industry proponent too. Alternatively, the corporation could take on the role of industry proponent and, utilising our land and access to water, be a hydrogen producer. Could procure solar panels, wind turbines, batteries, electrolysis equipment, etc., to produce hydrogen. With the development of the hydrogen industry, the corporation's involvement could be less direct. The corporation could be an off-taker of water from an industry proponent that builds a new desalination plant to supply their electrolysis unit and has excess capacity that the corporation could take advantage of. Conversely, the corporation could benefit from having a large off-taker from its next desalination plant. This could be particularly advantageous in achieving an off-balance sheet outcome for that investment. Water Corporation has recently updated its vision, goals, and objectives. Work is currently underway to determine where we should play in this important emerging market and understand the value the Water Corporation brings to the table. So, why is the Water Corporation involved in the Hazer project? Through the agreements with Hazer, we sell them biogas, thereby generating revenue for the corporation. By not flaring the biogas and producing hydrogen and graphite, we avoid production of CO2, which is good for the environment. A good way to keep abreast of the latest developments in an emerging industry is to do a project in the sector. Through the collaboration with Hazer, we have kept up to date with the latest developments in the hydrogen industry. Being involved in the Hazer project demonstrates our innovative thinking to our stakeholders, customers, and owner, which we'll all appreciate as being an important thing to do in this day and age. In addition, being involved supports the strategies detailed on the previous slide, so we demonstrate that we're a good corporate citizen for the state of WA. The ready availability of hydrogen at our sites could help Water Corporation decarbonise its supply chain. We could convert our trucks and utes to hydrogen fuel cells to reduce diesel consumption. Also, we could replace diesel generators in drinking water catchment areas with hydrogen tanks and fuel cells to remove the hydrocarbon contamination risk. The development of the project could help diversify WA's industry. We all know WA is renowned for its export of minerals, and iron ore specifically. For example, for this project, graphite could be used in batteries and the hydrogen exported. A key feature of this technology is that it does not increase water demand, which is particularly applicable in an environment significantly impacted by climate change. In the southwest of Australia, we have experienced an 80% reduction in stream flow into our dams as a result of climate change. Overall, we believe this project is a great news story for WA. It is technology developed at the University of Western Australia. It uses a well-known WA product as its sacrificial catalyst, iron ore. And it will be proven to be commercially viable at a WA water resource recovery facility. A great trifecta, I hope you would agree. Thank you for your attention, and I'll now hand over Luc for his presentation.
Thank you, Russell, for your input. I'd now like to welcome our second speaker, Luc Kox. Luc has 20 years of experience in the water, oil and gas and renewable energy sectors, with extensive experience in international business, development and commercial management. As commercial manager with Hazer, Luc is responsible for the commercialisation and growth of the company by identifying and developing opportunities for applications of the Hazer process and the associated partnerships both in Australia and overseas. Please welcome Luc Kox.
Thank you for the introduction. I'm truly excited to be on this virtual stage. Thank you to Engineers Australia for hosting this webinar, and for the partnership with Water Corporation, who are supporting this event. Thank you for the invitation by Water Corporation to join on this truly exciting webinar, hopefully, about an exciting project that's currently taking place. So Hazer Group Limited is a technology development company focused on the commercialization of the Hazer process. We're listed on the ASX, and that's why I'll have to show you this slide as a disclaimer. In brief, it says that I'm not a financial advisor. If you believe you need to seek financial advice, seek it from a professional. Otherwise, we would welcome your support as a shareholder of Hazer. In today's webinar, I'd like to essentially talk about four topics. First, I'd like to give you an introduction about the Hazer process. Then the focus will be on the Hazer commercial demonstration plant, which Russell already indicated. I'd like to also briefly touch on a proposed project in Canada that we're working on, and then provide a brief introduction on our research and development program around our graphitic carbon product. So why hydrogen? Russell has already given an introduction on what's going on in Australia in recent years, especially since we started our conversations back in 2018. The conversations between Water Corporation and Hazer started for this project. But in recent years, there's been an enormous evolution and development of the interest in hydrogen globally. I think it's fair to say that it's widely accepted that decarbonization needs to happen. We need to decarbonize our energy consumption, energy usage. It's also widely accepted now that hydrogen will play a very material role in that. Last year, the UN Climate Change Conference, or COP26, reaffirmed the global commitment to reach net zero emissions by 2050. And around 75 countries have now signed up to that to reach those targets for decarbonization. Hydrogen will play a role in that, a major role. In particular, we believe in sectors or industries that are traditionally hard to abate or hard to decarbonize. Examples of those are heavy industries, steel making, manufacturing of chemicals, and heavy transport. What many people don't realize is that currently hydrogen is already used in a lot of industrial applications in particular. Examples of that are the refining of petroleum and also the production of fertilizer. This is typically done with a process called steam methane reforming, where a methane molecule, CH4, is split into the hydrogen people are after, but it also comes with a significant emission of CO2, which is obviously undesirable if we're wanting to decarbonize. A process that currently has been obtaining a lot of interest and a lot of excitement, in particular in Australia and other countries that are blessed with abundant renewable resources, is the splitting of water electrolysis. So it's a splitting of water into hydrogen and oxygen. That is a technology that does require a very significant amount of energy, renewable energy, to make this low emissions hydrogen. Enter the Hazer process, what we're here to talk about today. So the Hazer process is based on a process called thermocatalytic methane decomposition, or the splitting of methane over a catalyst. So we start with a methane molecule consisting of CH4, consisting of carbon and hydrogen. Through the Hazer process, we convert that methane to hydrogen and graphite as a solid carbon. So there's no CO2 emissions from the process as such. Rather, we convert the carbon to a solid carbon product. So it's an inherent form of carbon capture and storage, or carbon capture and utilization, if you like. Thermocatalytic methane decomposition is not new as such. What happened, though, is that in the universities and companies working on these technologies and applying these technologies, we're using more and more exotic materials as the process catalyst, which means it got more and more expensive to produce the hydrogen and the graphitic carbon product. So what is the most novel thing about the Hazer process is the use of an abundant, relatively inexpensive iron ore product as a catalyst. As Russell mentioned, a very Australian, or very WA approach as well. So that brings me to the history, and this is where I'd like to spend a bit of time to talk you through the evolution of the technology in recent years. So Hazer, this is a fun fact, Hazer name actually stands for Hydrogen and Zero Emissions Research, which was the placeholder for the research that was conducted in the early 2000s at the University of Western Australia, headed up by Dr. Andrew Cunijo, my good colleague here at Hazer, who is currently our CTO, Chief Technical Officer. He conducted his PhD research on what is now the Hazer process. So the company was formed in 2010 with all the intellectual property rights transferring from the university to the company. And the company listed on the Australian Stock Exchange in 2015, which is relatively early, considering at that point there was only a limited research was done. In the years following, so in 2015 onwards, bench testing was conducted at the University of Sydney, and that evolved into pilot plant testing at St. Mary's in Sydney, and later on in Kwinana in 2019. And by that time, after those pilot tests were successfully concluded, Hazer decided to develop the next scale project to scale up the technology and to demonstrate the potential to scale it up. And this is where the commercial demonstration plant project was initiated. So this is where our collaboration with Water Corporation started, as Russell just mentioned in his presentation. In late 2018, Russell and I got together and started discussing this potential project. That evolved into signing an MOU in May 2019, and that's where the project started to become a real project. Fast forward a little bit through the course of 2019, and then we successfully applied with the Australian Renewable Energy Agency for grant funding for this project. We successfully applied for $9.4 million from ARENA funding. Then we executed the binding collaboration agreement with Water Corporation and a gas supply agreement in which Water Corporation supplies the biogas to Hazer for the operation of the plant. That was all necessary for us as Hazer to announce the final investment decision in July 2020. So that's when the project was finally announced to go ahead. I will go into the project in a lot more detail in the next coming slides. In this timeline, I'd also like to highlight that earlier this year, in February and in April 2022, we announced a proposed project in Canada, for which we have now also successfully received funding from the province of British Columbia as a project group, but more on that later on. As I mentioned previously, the Hazer process uses methane as a feedstock. That methane can come from fossil fuel origin, natural gas, or it can come from an organic source, biogas. And biogas is remarkably ubiquitous. There's quite a bit around us, and people don't always realize this, but landfills and wastewater treatment plants are significant sources of this biogas, this organic methane. So if we use that feedstock in the Hazer process to convert the methane to hydrogen and graphite, something really interesting happens because it's an organic feedstock, and we remove the carbon via the graphite. The system becomes carbon negative. So carbon negative is not a correct technical term, but it does capture the essence of what's happening. The correct term would be carbon abatement. So in a situation where you have biogas as a feedstock, run it through the Hazer process, you can actually offset significant emissions from existing operations as a user of hydrogen and graphite products. So that's why we thought that was a good idea to use biogas as a feedstock. It also enabled us to apply for the ARENA funding that I mentioned previously. So that's where the conversations with Water Corporation started and resulted in the project that we're talking about today, the Hazer Commercial Demonstration Project. The plant is located at the existing wastewater recovery facility at Woodman Point here in Western Australia and in the southern metropolitan area of Perth. As Russell has shown you a video of the site, so our plant is located on the premises, on the site of the Water Corporation. So we're very grateful for this collaboration with Water Corporation. I have said this many times, Russell, and I'll say it again. It's been a true pleasure working with yourself and many others in the Water Corporation. And as Hazer, we are very grateful for the support and the facilitation of our project to enable us to take a next step in our development. So to go into the detail of the project, the hydrogen production capacity is approximately 100 tons per annum of hydrogen. To give you an idea, that's enough fuel for approximately 15 buses. So it's not insignificant. It's a good size for us to step up from pilot to demonstration as a stepping stone to first generation commercial scale plants. In addition to hydrogen, it will produce approximately 380 tons per annum of graphitic carbon product. And I'll go into that a little bit later on. And whilst this is a 3D, which is good, I'm very pleased to show you the next picture, because this is actually what the plant looks like today. As you can see, this picture was taken on the 3rd of June, which is fairly recent. And as you can see, the plant is construction is materially complete, with mechanical, electrical verification going on at this very minute. Will be finalized throughout June, and we expect the plant to be completed and available for initial cold testing phase of operations by 30th of June, so end of this financial year. Going forward, our program comprises of 2 phases of testing before commencing full operations later on in the year. Initial cold testing phase will commence at the end of June, as I just mentioned, and this will focus on the material handling and control system aspects of the plant, and will utilize a temporary cold reactor. It's hard to identify in this picture, but it's actually already installed on site. It looks like one of the legs that you can see in the main structure there, but it's been installed. And then the second phase will consist of the full hot testing of the plant, which will occur towards the end of 2022 with the installation of the hot wall reactor. This reactor is currently being fabricated after a manufacturing defect was identified in the initial reactor. We expect that reactor to arrive on site in the 4th quarter of 2022 calendar year, so by the end of this year. Just to do a quick run through of what you're seeing here. So this is, again, located on the Woodman Point water resource recovery facility in Perth. To the left of this picture is where the wastewater treatment plant is located. So we receive via a pipeline, raw biogas from the anaerobic digestion process that Russell spoke about. On the left here, you see the biogas purification packages. That's the removal of H2S, siloxanes, and CO2. Then the gas flows through to the main structure where the reaction will take place, I should say, in the reactor. And after the gas has been transformed to hydrogen and graphite, the solid gas mixture is separated into graphitic carbon, the graphite, and hydrogen, which is obviously captured. The shed here on the next to the main reactor is the storage for catalyst and storage of graphite. And the big green box on the very right is the electrical the switch room with the motor control centers and the plant controls. Now onto the Burrard Hazer hydrogen project. This project is a proposed project that we announced during the year in February and in April 2022, respectively. We're working together with two very well-established partners for that project, Suncor Inc. and Fortis BC, both very established energy companies in British Columbia in Canada. The project focuses on a 2,500 ton per annum Hazer production facility that will also produce approximately 9,000 tons per annum of graphitic carbon product. The feedstock will be natural gas supplied by Fortis BC. The hydrogen will be injected into the natural gas distribution grid. And we're very pleased to be working with these very professional, well-established partners for this project. And we're also pleased that we successfully collectively applied for funding with the province of British Columbia. We secured 8 million Canadian dollars out of a budget of approximately 11 million dollars Canadian for the pre-FID activities of the project. So pre-FID means pre-final investment decision. So this covers things like initial feasibility study, the front-end engineering design work, permitting, and the assessment of how to blend the hydrogen into the natural gas system. So that's all coming together very well. As an indicative timeline, I can confirm, as we've previously announced, that the initial feasibility study has already commenced earlier in this year. The project group is targeting a final investment decision for this project in mid-2023, and the ready for startup date is a target date of 2025. So very exciting times for Hazer. This will be the next step in the development of our technology. A lot of talk about hydrogen would also be very appropriate to talk about graphite, the other product that is produced by the Hazer process. The Hazer graphite product is a very versatile and unique product that is potentially applicable in a wide range of applications. Graphite and graphitic carbon are very commonly applied commodities in a range of industrial applications, and I'll go into the potential applications in a little bit. But it's quite a large and growing market because, again, like hydrogen, we believe graphite will also play a major role going forward in the electrification and the decarbonization of our society. So as Hazer, in terms of research and development, what we are doing is essentially covering two things. First of all, it's the process optimization and catalyst selection research. The other part is functionalization research, which includes purification, but also focuses on the potential applications of the Hazer graphite, be it in its unpurified form. Out of the reactor, we achieve 80 to 95% purity for the graphitic carbon product, or in a purified form. We have previously shown that at lab scale, we can achieve in excess of 99% purity for the graphite product. So that's where a lot of our research activities are still going into. We're also developing our own in-house purification technology that focuses on the specific purification of Hazer graphite with its specific characteristics. The potential applications, as I mentioned, are quite wide-ranging. That ranges from advanced materials energy storage, metals processing, lubricants, and water treatment, which is a nice loop back to Russell's presentation before. We have reason to believe that Hazer graphite is particularly suitable for the purification of wastewater. So that could be an interesting example of circular economy as well, to use biogas to produce graphitic carbon product that could be used in water purification. What is important to note is that a lot of these organizations that use graphitic carbon products often have a strong desire to test the graphitic product going into the process at a very large or at a decent scale. For us, relatively large, coming from where we're coming from an R&D pilot process point of view. Typically, the questions we get is a number of tons for testing. So we will be progressing those discussions and that kind of testing as soon as the CDP comes online, as I mentioned before, the target date being the end of the calendar year into 2023 for the graphite trials. So as a summary, hopefully I've been able to give you an introduction on the Hazer technology, focused on the commercial demonstration project together with Water Corporation. I've told you about the MOU in Canada. We continue to focus on research and development as the core competence in our company. And with that, I'd like to wrap up my presentation and move on to the Q&A session.
Thank you, Luc, for your insightful presentation. Now, before we jump into our Q&A this afternoon, I would like to acknowledge the keen interest in this topic that we've received. We've had over 1,600 registrations, and they have come from across Australia, Asia, Middle East, Africa, Europe, and America, a truly global audience today. Now, it is your time as our audience to get involved, so please ask our speakers your questions via the chat box, and I can see that quite a few have already come through. But don't forget to let me know who your question is directed to. And I would like to say a big thank you to everyone who has already submitted questions while registering for today. And what we might do is kick off with some of those questions. So the first question which has come through has been from Ranjani in Asia. Now, I'll direct this question to our panel, so to both Luc and Russell. And Ranjani's question is, what are the end uses of wastewater from this process? Is there any plan to use the wastewater for electrolysis and produce hydrogen? So maybe who would like to kick off today? Russell, awesome.
Thanks, Megan. That's a great question. So maybe just to give a bit of background on the Woodman Point site and the Water Corporation more generally. So we look at providing fit-for-purpose water from the treated wastewater that we produce at our wastewater treatment plants. So, for example, a great example is Woodman Point, where we supply industrial water through our Kwinana Water Reclamation Plant, or QWERP as we like to refer to it as. And that supplies a number of industrial parties in the Kwinana industrial strip. And that takes treated wastewater, pushes it through reverse osmosis membranes to produce very high quality water that is supplied to those customers. And I think in my presentation, you'll remember that I talked about the mindset shift that the Water Corporation is trying to achieve through changing the name of our wastewater treatment plants, where we beneficially reuse some of the byproducts. And Woodman Point's a great example of this. So the byproducts that I'm talking about are biosolids. So they are transported to farms and used as a fertilizer. So 100% of the biosolids that are produced at Woodman Point are transported to farms and beneficially reused. We've already talked in some detail about the biogas, and you've heard what we use that for in the first instance. And in this trial, we're exploring other uses of that biogas as well. And the biogas also contains CO2. That's an interesting opportunity for the Water Corporation, because the corporation uses about 22 tonnes of CO2 a day. Now, you might say, well, that's an enormous amount of CO2, which it is. And why would you use that? So we use that in the production of drinking water from our desalination plants. So we've got 2 desalination plants, one at Biddingup and one at Kwinana. And as part of the repotabilisation of the water that comes through the membrane, because if you tasted the water that came through the membrane, you wouldn't be too impressed with it, but we repotablize it, add things to it, such as carbon dioxide, to make it more aesthetically pleasing. And the other one, just finally, is struvite, which is a magnesium ammonium phosphate compound, which is another good fertilizer that we could utilize and derive through the plant and sell to customers in Perth. And I think this also kind of touches on a theme through some of the questions that we've seen already, which is around the use of water in the Hazer process. So one of the things that attracted to us, and Luc mentioned it, was the fact that it doesn't require any water as part of the process. And in a drying climate such as the southeast of Australia, that's southwest of Australia, that's really, really important for us to be able to not have another impost on our water sources. So that's great.
Excellent. Luc, did you want to add to that?
Maybe only to re-emphasize that the Hazer process does not use water. It starts with methane molecules, which we split into hydrogen and graphitic carbon. And the process also doesn't produce any water. So there's no water involved with the Hazer process as such.
Okay, thanks. Luc, I do have a question for you. It has come from Lauren in New South Wales. Now, her question is, does the Hazer technology have the potential to be a game changer for the hydrogen industry as an alternative to more traditional, water-intensive hydrogen production technologies? Luc.
Well, thank you, Lauren from New South Wales. A good question. Game changer. That's, I guess, for others to say. I think we'd like to take a more humble approach. However, what I can share is that actually in late 2022 we won an industry award from the Energy Club in Western Australia. That is called the Game Changer Award. So people do believe that we have the potential to be a game changer. That also is, I think, confirmed by the interest we see in our technology, which is global interest. It's from within Australia, but also very much from outside Australia, and it also ties into the one of the other questions that we'll touch on in a minute.
Excellent, thanks, Luc. So the next question has come from Christopher in Queensland. So thanks, Christopher, for your question, and he has directed it to you both. Is the process and/or hardware patented? And can you recommend any peer-reviewed papers on this topic? So, Luc, did you want to take this one first?
Sure, thank you. Yes, is the short answer. The Hazer process is patented. What I tried to share in my presentation as well is that the research was initiated at the University of Western Australia here in Perth. And when the company was founded in 2010, all the IP, so all the intellectual property rights were wholly transferred to the company. So Hazer company currently owns a number of different patents across 4 patent families for the people interested in patent details. And we are progressing those applications in a wide range of jurisdictions. And as for those that are following Hazer, you see from time to time we share when patents are actually applied. But all the IP is owned by Hazer.
Excellent, thanks. Russell, did you have, I suppose, are you able to recommend any papers, any peer-reviewed papers on the topic, or did you want to add to that answer?
Yeah, so the Hazer Group website is a font of information. So if you're interested in the technology, I definitely recommend that as a source of information to hopefully answer all of your questions. So I know I work for the Water Corporation. I now sound like I work for Hazer Group, but you can probably tell through the conversations that we've been having and the presentations that we've got a very close relationship with Hazer, and it's great to see their technology progressing.
Excellent. Thank you both. I've got a question which has come in from Bettina in South Australia. And her question is, she's interested in more details about the catalyst, where it is made and how it contributes to the overall process. And then she's got, which reaction is it catalysing? So Russell or Luke, who wants to kick off with this one? I'll pick someone. Luke.
Yeah, I'm happy to take it. Thank you. So yeah, what I tried to say in the presentation as well, thermocatalytic methane decomposition has been around for quite a while, and the fact that we, as Hazer, use iron ore as a catalyst is the most novel bit. That's also registered in the patents, that very aspect, because it's abundant and widely available. So the short answer to the question is it's iron ore, wherever iron ore is produced. So that can be in Australia and other parts of the world. For details on the reaction, as Russell just mentioned, in general, I'd like to point out that on our website on hazergroup.com.au, you can find a lot of information. And specifically, there are two video animations that I believe explain the process, so the catalytic process in quite detail, quite well, and also the carbon negative potential of using biogas as a feedstock is shown in those videos. So it's iron ore, as it comes out of the ground, is used as a catalyst in the process.
Excellent, thank you. Russell?
I've got nothing more to add on that one. I think
Awesome.
Luke's answered that one well. Thank you.
We'll move on to the next question. We've received a couple of questions around scalability. And so just probably to summarise, how scalable is the technology from small regional remote communities to large mining campsites? And that question came through from Scott in WA.
So maybe Luke, if I have a crack, and then you can follow on with the Hazer perspective. So from the Water Corporation's perspective, there's a minimum size of plant that's required to produce before it becomes economically viable to make biogas. So Woodman Point, as I mentioned, has got a throughput of 145 MLD, and we produce biogas. The other plant that currently produces biogas is the Beanie Up Water Resource Recovery Facility, which has got a throughput of around 130,000 MLD. And we're in the process of considering digestion at our Subiaco Water Resource Recovery Facility, which is at just under 70,000 MLD at the moment. So in the 70 to 80, 90,000 MLD, that's the trigger from the Water Corporation's perspective for generating biogas, which is, as we've discussed, is the basis for the Hazer process as a renewable biogas or renewable methane source. So that's kind of where the Water Corporation is coming from. And then maybe Luke, you just want to talk about your development of the pilot to CDP, and then your collaboration in Canada.
Yeah, thank you, Russell. That's a very useful introduction, especially the fact of the almost a cutoff point, I guess, where you start to produce biogas at wastewater treatment plants. You need a decent scale to be able to produce that biogas. So that already addresses a fair bit of the market in that sense. In terms of the scale up of the technology, as I mentioned in the presentation, we've previously done pilot testing, which is a very modest scale. This commercial demonstration project is, you could call it a small industrial application of the process, 100 tons per annum of hydrogen production capacity. Then the next scale from a Hazer perspective is that scale of 2,500 tons per annum for the proposed project in Canada, which I mentioned. So maybe also useful to point out that in the course of over the course of 2021, we worked with engineering firm from Japan, Chiyoda Corporation, to provide us with engineering support and cost estimation of the next generation of Hazer plants in the 2,000 to 5,000 tons per annum bracket, both from using a biogas feedstock, but also a natural gas feedstock. There's no limitation necessarily technically on how large we can go, but we're following a staged approach in terms of increase of the capacity.
Excellent, thanks. Thank you to you both. The next questions come in from Daniel. So thanks, Daniel, for watching and for your question. His question is, the hydrogen industry works across a rainbow spectrum. Coal is brown, renewable energy is green. What colour is the Hazer process? So, Luc.
Yeah, thank you, Daniel. That's actually a really useful question. Indeed, the hydrogen industry and also the media tend to talk in colors, although that's starting to be acknowledged that that's not so useful anymore. Hazer hydrogen would be classified as turquoise, where you have a methane feedstock going in and you capture the carbon as in a solid form. However, the nuance there being, if we use biogas as a feedstock, it becomes carbon negative, as I mentioned in the presentation. So it becomes better than green hydrogen. So what color is that? What color is better than green? It's a bit of a silly question. So it's more appropriate to actually talk about carbon intensity and just put a number to it. You can be scientific. You can do the proper calculations and determine what the actual carbon footprint of your hydrogen is.
Excellent. Thanks, Luc. Now, Russell, the questions come through from Pete Bolt. He's watching today, and his question is, why is excess gas flared off? Can it not be used for energy or a heat source?
Great question, and probably seems strange that we would do that, and it's probably caused by the fact that we do a very low level of scrubbing on our biogas that comes through the digesters. And what that means is, for the 3 reciprocating engines which I mentioned, is that we have operating problems with those engines, because whilst we've got sufficient gas to run all 3 engines at any one time, the low level of scrubbing causes us issues with the operation of those engines, and so we typically have one engine out at any one time, and therefore we can't use the biogas there. We can't store it for a long period of time, so we have to flare it in that instance.
And then another question, sorry, just to kind of keep going with you, Russell. Sorry about that, a bit of a run. And this one's come from David Levy, and his question is, what happens to the CO2 stream? Is it vented or could it be captured?
That's a great question, and is the subject of a study at the moment that the Water Corporation is undertaking. As I mentioned, we use 22 tonnes of CO2 a day, so we've got a demand for that. Currently, as the biogas is currently used, we effectively let that CO2 stream go through, along with the methane, through the gas engines, and are expelled as part of the normal exhaust gases, or flared as part of the biogas where they're flared. So it kind of just at the moment just goes along for the ride, but we recognise that there's a significant value associated with that resource that is from a renewable source, and we can potentially take advantage of that for our own purposes.
Well, thanks, Russell. I'll just jump back to, I've got a question which is directed at both of you, and it came from Rathish in the Middle East. And his question is, what will be the expected market share of the hydrogen fuel produced by this method? Will it satisfy the demand and supply requirements compared to traditional hydrocarbon fuels? Luc, do you want to jump in with that one?
Sure. That's quite a big question, especially the last aspect. There's obviously, state the obvious, society, we use a lot of hydrocarbon-based fuels. Will the Hazer process be sufficient to replace all that fossil fuel existing conventional hydrocarbons? The short answer is no. I think that's unrealistic to think. What I tried to say in the presentation as well is that it's now widely acknowledged and understood that hydrogen will play a role in the decarbonization of society. It's not the silver bullet. There's no silver bullet. We will need, as society, we'll need all the toolboxes, all the tools in our toolbox, I should say, to decarbonize. We see that there's a consensus now in industry that hydrogen will likely have a role to play in the decarbonization of heavy industry. So traditionally hard to abate or hard to decarbonize sectors such as heavy industry, steel making, fertilizer production, heavy transport as well. So maybe not so much for passenger vehicles, but more for heavy transport, which is buses, trucks. Here in Australia and in Western Australia particularly, there's some interest in running mining haul trucks on hydrogen, where battery electric may have disadvantages and hydrogen may have advantages. So that's the type of applications where we believe hydrogen can definitely displace a lot of conventional hydrocarbon fuels. And as Hazer, we're looking to take a share of that market, obviously going forward.
Excellent. Thanks, Luc. Russell, did you want to add anything to that one?
Yeah. So maybe just to reiterate what I said in the presentation, which was the Water Corporation is keen to decarbonise our supply chain, and we use 6 million litres of diesel every year. So there's plenty of opportunity there. So we're keen to explore opportunities to use hydrogen for our trucks and our utes, and as Luc intimated, hydrogen is probably more applicable to the heavier side of vehicles than the lighter passenger vehicles, and also for our remote areas where we've got public drinking water catchment areas and we use diesel powered pumps to extract the water from groundwater. Now, the presence of diesel in the drinking water catchment is a risk, and I know there's many of you people out there that think, it's just a tank of fuel. What can go wrong? I think our water quality people will be able to provide you quite a thick book of examples and case studies of just what can go wrong by just people doing the very simple act of filling a diesel tank in a water catchment area. So if we can replace that with a hydrogen tank attached to a fuel cell, that might well be the solution which assists us to address that risk, and to prove to our regulator that we are doing something to address that risk. So it's an exciting part of the project.
Thanks, Russell. And kind of on the topic, and a question came through from Daniel, and I'm hoping, Russell, that you'd be happy to answer this question. But his question is, have you been approached by the community about risks? And so what is your recommended response to these concerns?
Absolutely. This is a key consideration for the Water Corporation when we do anything on any of our sites. And Woodman Point has what we refer to as a CRG, or a customer reference group. And I'm absolutely delighted to be able to tell you that our customer reference group has been nothing but supportive of the Hazer project on Woodman Point. And we have taken a number of opportunities, and Luc's presented to them at least 2 to 3 times. I've presented probably to them about 4 to 5 times. And I think that's the key, is if you bring the community with you on your journey, then they understand, and you can provide them the information for them to make a decision as to whether they'll support or not support a project. Then they more than often than not make the right decision, which is to support the project. And we're really pleased with the customer engagement that we've had at Woodman Point on this project.
Thanks, Russell. Another question is from David, and we're getting a lot of questions coming through live. Thank you to our audience. So his question is, the biogas feedstock is a mixture of methane and CO2. What happens to the CO2 in the Hazer process? Is it captured before or after the methane conversion to H2 and graphite, or vented? And that one's from David Blacklock. So Russell, you might want to take that, and then Luc to add in?
Yep. So from the Water Corporation's perspective, we do a very low level of scrubbing. So we don't actually extract any of the 2 main components, whether that be methane or CO2, and then we pass that on to Hazer Group as for use in their process. And maybe Luc, you'd like to describe what happens when it gets to your side of the fence.
Yeah, thanks, Russell. So yeah, we indeed start with the raw biogas as it's presented to us from the biogas buffer tanks owned and operated by the Water Corporation, and we have quite an extensive biogas purification step. We want to remove all those impurities that can have an impact on the process potentially. CO2 is an example. Would take up reactor space. So it would be an inefficiency on the process to have it in the process. So we prefer to remove it from the process. As Russell said, that there is potential to use that CO2 in industrial applications. Should also be noted that it's biogenic CO2. So in Australia, that doesn't count against CO2 emissions because it's short cycle CO2 versus long cycle carbon. And yeah, that's about it, I think.
Thanks, Luc. Russell, I have another question from you. Oh, again from David Blacklock. So David's got a few questions. What sort of volume of H2 would you produce from this wastewater plant? Is it a significant source of H2 against a likely future demand?
That's another really good question. So from our current arrangement with Hazer, we provide them roughly a fifth of the production of biogas from the plant, and as I said, it's about 900 normal meters cubed of biogas produced per hour at the plant, and roughly a fifth of that goes to Hazer to produce their 100 tons per year. So if we were to go to full production, we could potentially increase that from 100 tons to 500 tons. And at 100 tons, you're probably talking 5 to 6 buses, running 5 to 6 buses throughout the year. So it's not a huge amount, but it's not a small amount of hydrogen. And if we went to 5 times that, then we're at 25 to 30 buses, which is not an insignificant number of utes, which we use quite a lot of, or small trucks. Interestingly, at Woodman Point, we've got an expansion project which we're exploring at the moment, which is likely to increase the biogas production by another 30%. So we'd be able to go to sort of 6.5 times what we currently supply to Hazer, and therefore we're up around the 6.5, 650 tonnes per year. So yeah, it's not. We certainly wouldn't be exporting that volume, but it's certainly helpful, and our close proximity to Kwinana Industrial Estate could be another source or another customer for hydrogen as they transition to a hydrogen economy as well.
Excellent.
Maybe if I can, Megan, sorry to build on that. The production capacity for the CDP, 100 tons per annum, the number is even slightly higher, I think, than what Russell indicated. 100 tons per annum is enough fuel to power about 10 to 15 buses. So that's a very modest scale Hazer process plant. We need 2 million normal cubic meters of biogas to power that plant. So we can indeed go a lot larger, potentially on Woodman Point. Wastewater treatment plants, but also landfills produce a lot of biogas. And I wholeheartedly concur with the point Russell made. You typically find there's a geographical advantage as well. You find landfills and wastewater treatment plants in the periphery of populated areas, right? That's where you find those type of wastewater treatment plants, which is also where you tend to find industrial activity or fleet operators that could potentially benefit from having a source of very low, I don't want to use a color, but very green, very low emissions hydrogen close to their point of use, which is always the key with hydrogen. You want to produce hydrogen as close as possible to the point of use, because it's energy intensive and cost intensive to transport hydrogen.
Excellent, thank you both. We've had a question come through from Cameron Matters, and his question is, what type of control system is required for this process? Maybe, did anyone want to jump in on that one? Happy to move on if you want me to move on.
Well, look, I can say this. I'm originally a civil engineer, so control software is definitely not my forte. It's a complex gas processing process. So whatever the control systems are that you'd expect with such a plant, that's what it is.
It might be another topic in itself.
So
sure. I'll move on to the next question. Holistically, how does it compare with producing hydrogen gas from recycled water to the production of hydrogen from biogas? Biogas from the anaerobic digesters could be used for cogeneration, generating electricity, which could be used to operate the Woodman STP. So how does it compare? Russell, did you want to kick off with that one?
Yeah, so it's probably worth saying that the point we've made before, which is around that the Hazer Group as it currently stands does not utilise water, and that's an advantage in a drying climate. So to put that to one side. In terms of the difference of using recycled water through electrolysis to produce hydrogen, we've all seen, I think, the recent publications in terms of the volume of renewable energy to power something like that is huge, and to split those hydrogen and oxygen atoms is quite considerable. And then when you compare that to utilising biogas to produce hydrogen, the information is probably commercially confidence for Luc, so you'll probably be unlikely to get that, but I suspect that it's a lower amount of energy required to split the CH4 through that thermal decomposition process, than a catalytic decomposition process for methane, than it is for electrolysis. And so I think this process is probably more energy efficient when you compare it to electrolysis itself.
Luc, did you want me to go on to the next question?
Yeah, sure. I've got nothing to add. It's very accurate.
There's been a little bit of interest if there are any further Water Corporation Hazer projects planned in the future.
So we've certainly talked about it, Luc and myself, and we are both eager to see the outcome of the CBP and where we get to there. I don't think I'm going to be giving away too much to say the contract allows us for further discussions on future developments. So we're certainly keen to explore the technology into the future and to support it where we possibly can. But at the moment, there's nothing on the cards, but that doesn't mean to say that there won't be at some point in the future.
Excellent. Luc, a question has come through from an audience who's currently Abby from Oregon in the USA. And the question is, what are the advantages that Perth has that other places don't to make a project like the one you demonstrated successful? Can this project be implemented anywhere in the US, for example?
Yeah, that's a great question. Thank you. And I think Megan may have mentioned this in her introduction, but if you haven't picked it up already, my accent is Dutch, so I'm originally from Holland. I mentioned that because I'm obviously heavily involved with all the international activities for around Hazer. Why Perth is chosen for this project is the fact that the company is based here. So the company, the technology, as Russell also indicated, comes from the University of Western Australia. The company is located here in Perth. For us, just the logistics of having the project in our backyard is very convenient. It's very useful. We wanted to keep this in Australia, also in terms of the funding with ARENA. Often we see technologies such as Hazer get picked up quite early on and leave Australia as such and get further developed outside of Australia. We were very keen to not have that done to Hazer, so we wanted to take this next step in Australia. The Woodman Point wastewater treatment plant is only located 40 minutes away from the Perth CBD, so which is just very convenient. Also for us to use this project as a showcase when we have people visiting Perth, which by the way is a fabulous place to live and to do any projects. That's a side topic. It's good for us to showcase the plant and use it as an example. And indeed, this kind of technology can be applied anywhere in the world. So in the US, what I can speak about is our geographical focus as Hazer is definitely North America and Canada. I mentioned the Canada project in this presentation, Europe and parts of Asia, and of course Australia, where we are located. But the technology can be applied anywhere.
Excellent, thank you. Look, I think we're starting to come to the end of our session today, and there is one particular question that I would love to end with because I think it's really important, especially as Engineers Australia. I think these are, the information that talking to you both as the experts. And this question came from Cristofaro in WA. And the question was, what kind of professional skills and qualifications are needed now or in the future to support growth of this sector? So, Luc, did you want to kick off?
Yeah, sure. That's a very important question, I think, especially for those people attending today's session. If you have an interest in the renewable energy industry, or even specifically hydrogen, I can wholeheartedly encourage you to get on board, to see in your current organization if you have access to that kind of activity. Get involved. It's incredibly exciting. There's an enormous amount of activity going on across industries. In terms of the skills that are required, I think a lot of it is obviously about renewable energy, electrification, maybe also process knowledge in terms of how to change existing processes, industrial processes, manufacturing processes from conventional methods to renewable based. So that brings in a whole suite of other skills and experience. But I can totally encourage everyone to do so, because it's an incredibly important and interesting and very dynamic industry. Maybe Russell, you can add some from your perspective.
Yeah, sure. So, and a question on my last slide was kind of, why is the Water Corporation involved? Because you might think that wastewater is relatively simple, and there's a few of my colleagues on the presentation in the audience who would significantly disagree with you, and I would agree with them that it's not a very simple process, because when it goes wrong, you can't turn it off. We need to accept wastewater 24 hours a day, 7 days a week. But in terms of the skill sets to be involved in this, I think it's starting with a growth mindset. I think that's key. And then the second is that process and chemical engineering basis, which allows us to then optimize our biogas production in an environmental way, and store and keep that biogas and utilize it in as environmentally sustainable way as we can. So it's changing from just, you come to the Water Corporation, you might be a mechanical or electrical engineer, and you do things on pumps and switchboards and things like that. The Water Corporation has a much wider remit, and this is just one example of a project where process engineers, chemical engineers are really important for us to take advantage of these opportunities that the misnomer of wastewater is providing to us.
Excellent. Look, that's all time that we have for today. So please join me once again in thanking our presenters, Luc Kox and Russell Lamb, for their time and their input today. I would also like to thank Engineers Australia's industry partner, Water Corporation, for their support. Now, if you could please complete the short feedback form, which is linked in the description box below, that helps us to improve and plan for future sessions. So finally, thank you again for your time today, and I look forward to seeing you at our next Thought Leaders event. Thank you.